Mr. Duffy. Welcome to chemistry. For today's lesson, we're going to be talking about some rules for electron configurations. Electron configurations you can kind of think about as the addresses for the electrons in an atom. In previous lessons last week, we talked about quantum numbers, and quantum numbers are the parts of the address. So we're just learning how to write the address for the atom's electrons. To do that, again, we have to know some rules, and that's what our lessons are going to be about today. So let's go ahead and get started. There are three rules for filling electron orbitals, or giving basically the atom the electron its quantum numbers. First rule is what we call the Aufbau principle. Electrons are added to the lowest energy orbitals first before they move up to a higher energy orbital. Okay. Basically, it's just we'll go over each one of these individually a little bit more. Basically, it's just saying that electrons want to be as low energy as possible, and that's really the same as like the Bohr model. We started at the lowest energy, closest to the nucleus, and then moved our way up from there. Okay? The next rule is called the Pauli exclusion principle. It says basically each orbital can only hold a maximum of 2 electrons, and in that orbital they have to be moving in opposite directions, spinning in opposite directions. We talked about the magnetic spin quantum number, and that would be what the Pauli exclusion principle is referring to. Finally is Hund's rule. Hund's rule is the electrons occupy equal energy orbitals so that the maximum number of unpaired electrons is the result. Okay. And again, I will talk about each one of these rules individually, but let's start with the Pauli exclusion principle. The Pauli exclusion principle says that, again, each orbital must only hold 2 electrons and they must have opposite spins. This basically means that every electron is going to have its own set of 4 unique quantum numbers. So every electron's quantum numbers are going to be unique. So basically, again, every orbital can only hold 2 electrons, and one needs to be spinning up and one needs to be spinning down. We say plus half, minus half. That would be the Pauli exclusion principle. The Aufbau rule, or Aufbau principle, I've got an energy diagram on the right. Basically, electrons fill the lowest energy orbitals first before moving up to higher orbitals. This is, again, exactly the same as the Bohr model's concept. We started at the lowest, the closest to the nucleus, and moved our way out from there. Okay, and that's exactly what's going on here with the Aufbau principle. We're starting at the lowest energy and moving our way up. Sometimes this is called the lazy tenant rule. If you think of this energy diagram on the right as being kind of like a hotel or apartment complex, the tenants in this apartment complex, the electrons, are lazy. They don't want to walk up the stairs. Maybe there's no elevator, so they don't want to walk up the stairs if they don't have to, and so they want to fill the lowest floors first before the higher floors get filled up. And that's the Aufbau principle. And Hund's rule, the third rule, is within each sublevel, you place 1 electron per orbital before pairing them up. So basically, we have equivalent orbitals. They don't sit together on the bus. They each take their own seat, and then if they have to fill up, then they fill up. So according to Hund's rule, the diagram on the left is wrong because there's an empty bus seat, basically. And you want to spread those electrons out as much as possible to fill all the empty bus seats before starting to pair them up. The correct one is on the right, where we have, again, they each filled up individually, and then at the end, somebody had to pair up and had to sit together on the bus. And that's what electrons want to do too. They want to keep themselves apart as much as possible until they have to pair up. Again, they're going to do that as opposed to moving up to a higher level. They're going to, again, pair up before they would move up to a higher level. But these orbitals, the sublevel, is they're all equivalent energy. So they're going to, again, stay in equivalent energy to the sublevel, filling each orbital individually before then pairing up. So let's look at an energy level diagram of an atom that has lots of electrons. Actually, we're going to look at hydrogen first, which only has 1, but we're going to look at lots of different electrons in this diagram. What I'm going to put across on the right is the Bohr model, which we've talked about before. The nucleus is in the center, we've got those rings around the outside, and so forth. And we're going to see that it has some similarities, the Bohr model does, to the energy diagram on the left. But there are differences. And again, that's where we're going to. We're moving away from the Bohr model and trying to explain where the electrons are using a more complex, the quantum model. So let's start with hydrogen. Hydrogen has one electron, and according to the alpha principle, we want to start on the lowest energy possible, and that would be the 1s orbital closest to the nucleus. The Bohr model on the right, you can obviously see the exact same thing. We're just starting at the first energy level closest to the nucleus, one electron goes in it. Okay, now going to helium. Helium has two electrons, and that first energy level can hold two electrons. But notice, according to our arbitrary energy scale, that they have to be moving in opposite direction. That's the Pauli exclusion principle. So on the left side, we have an up arrow and a down arrow. They're in the same orbital. They're in the same energy level, but they're moving in opposite directions. They have different set of quantum numbers. The next element we have is lithium. And as you can kind of see, that helium is filled up. There's only two electrons can hold in each orbital. Um, so after that orbital is full, now we have three electrons. Lithium's next electron has to go up to the next energy level, the second energy level, the 2s energy level. That is an up arrow. And you can see again the Bohr model kind of still moving along the way we would expect. That electron had to move out to the second ring around the nucleus. Okay, so really haven't diverged much from the Bohr model. We're going to take a couple more steps to carbon. Carbon has 6 electrons, and you can kind of see that right now. The arbitrary energy diagram here on the left, um, with 4 electrons in it. They paired up in the 2s, and they stayed separate according to Hund's rule in the 2p. So the 2s orbital actually has lower energy than the 2p orbital does. So they fill up the 2s before moving up to the 2p, but when they have to pair up, they do pair up and down. And the Bohr model over here on the right, you can kind of see that's a little bit different from what we've done in the past. We kept them all separate until we half filled the energy level, and then we started pairing them up. And again, that's not quite exactly, the Bohr model does a good job most of the time, but it does not explain the quantum numbers perfectly. Um, and that's where the energy scale, the orbital energy diagram is doing a much better job at showing you what's actually going on with those electrons. Okay, now I'm moving on to nitrogen, just one more electron. Nitrogen here, again, according to Hund's rule, they keep unpaired electrons until they have to start pairing up. And right now, again, they do not have to start pairing up. But again, according to Bohr's model, this is where they started to pair up. Again, not really quite the correct picture of what was actually going on in the atom. Aluminum would be our next element. Aluminum has 13 electrons. You can see that the 2p has now been filled up entirely from nitrogens, and then the 3s was filled, and then it leaves one electron in the 3p energy level. You can see again, according to the Bohr model, it really kind of looks exactly the same. What we would expect the Bohr model to look like is that we have 3 electrons kind of separate in the Bohr model in the third energy level. But again, in reality, one of those, 2 of those electrons are really paired up, one up and one down in the 3s. Okay, let's move on to argon. Argon is going to fill that entirely with 18 electrons, and the whole 3s and 3p energy levels, the orbitals, are all filled. And the Bohr model, you can see they're paired up in that third energy level too. Okay, so nothing's really different there. The Bohr model was really, again, it was okay at elements to about this point in time, but after this point in time, it really diverged and isn't really the best model to use anymore. And that's where we go to iron. Iron fills up its 4s energy level, 4s2, one up, one down, and then they move into the 3d energy level. 1, 2, 3, 4, 5, the 3d energy level. And again, they stay separate until they had to pair up. And again, you have one pair in the 3d. Third energy level, the D shape, and again, up arrows, positive half spins. And finally, I'm going to show you lanthanum. Lanthanum is a lot of electrons. Um, didn't really look that one up to see how many there were before this video, but you kind of see again, the Bohr model is really not great at explaining what's going on here. So many electrons. The energy level diagram is really doing a much better job of um, where the electrons actually are located around the nucleus. Okay, so the energy level diagram, these rules that we're kind of following are really trying to explain where the electrons are around the nucleus. Now, the diagram is great, but it takes up a lot of space and it's a lot to look at. Um, Another way to kind of look at it is what's called an orbital notation. And it just takes basically the diagram and puts it left to right. And again, instead of going, having a big chart here, what we now have is again just a kind of a left to right. These are the orbital notations, where the electrons are, just kind of written out in a line. Still a lot of work. And so an electron configuration would be much better, and we're going to learn how to write those a little bit later on in another video. But let me just show you that. The orbital diagram, again, takes basically an atom, however many electrons it has, and puts them into boxes, just in a row from left to right. Again, still following the three rules for filling in electrons. But electron configuration takes that orbital diagram and kind of combines it down, condenses it. So hopefully in this video you learned how to fill up orbitals according to the three rules um, for filling orbitals. And in later videos we're going to again learn how to take those orbitals and condense them down into an electron configuration. So thank you very much for watching.